Finally, we need to talk about the normal random variable. The normal random variable is one of the most important random variables in the probability theory, and it is also used very frequently in statistical studies, and it is also a commonly used probability distribution in simulation modeling. Now, this random variable has two parameters, the location parameter and the scale parameter. The location parameter determines the central tendency of that random variable, and it basically resides in the middle of the symmetric PDF of normal random variable, and that PDF has a shape that looks like the bell curve, and the cumulative distribution function looks like an S shape here. Another parameter is this sigma square value, or sometimes we use sigma itself as a parameter. It is called the scale parameter. And the PDF is defined as follows for all the real numbers. However, unfortunately, it is impossible to integrate this PDF from -infinity to a certain x value. Therefore, the CDF is not available. So if CDF is not available, what we are going to do is we are going to calculate this CDF numerically using numerical integration methods to certain values over a table, and when we intend to look for a certain probability, we are going to search that probability from that table. Now, the expected value and the variance of normal random variable are basically equal to its location and scale parameters. The expected value is equal to mu, and the variance is equal to sigma square. Now, what we are going to do is, since the CDF is not available, we are going to say that the normal random variables are linearly transformed to each other, or in other words, when you take a linear function of a normal random variable, again you get another normal random variable. So normal random variables do not lose their probabilistic distribution properties when they are linearly transformed. Now, by applying a certain linear transformation like this, a normal random variable will be standardized. Since the expected value of x is equal to mu, if you subtract mu from x and divide it to anything, then the expected value of the output will be 0. And the variance of x minus mu over sigma is equal to 1. Okay, because the multiplier term 1 over sigma can get out of the variance as squared, and the variance of z is just going to be equal to the variance of x divided by sigma square, and the variance of x is sigma square as well. Therefore, the variance of z would be equal to 1. And since we know that the normal random variables do not lose their probabilistic properties up to linear transformation, the z random variable is going to be a standard normal random variable under these parameter settings. So we are going to calculate the certain CDF values for a standard normal random variable and store them on a table, a CDF table, a cumulative distribution table. And when we want to solve a probability question or probability statement related to any normal random variable, we are going to convert this statement into a statement that is related to a standard normal random variable and search for the probability through that table. So this is the procedure that we are going to apply. Here is the practice. It says the body weight of male students in Özyeğin University is normally distributed with 78 kilogram mean and 25 kilogram square variance. So according to the question, if we randomly select a male student from Özyeğin University, the body weight is going to be normally distributed with location parameter or the expected value or the mean of 78 kilograms, and the variance sigma square is going to be 25, or sigma is going to be equal to square root of 25, which is 5. The question is asking, what is the probability of a randomly selected male student to weigh less than 69.75 kilograms? So the question is asking me this, what is the probability of a randomly selected male student's weight, which is denoted by random variable x, to be less than or equal to 69.75? And that is going to be computed by standardizing this probability statement. And how do we standardize it? So as you can see from the previous page, we can standardize a normal random variable by subtracting its location parameter and dividing it to sigma value, the square root of sigma square. And we know that we need to subtract mu from x and divide it to sigma, and we are going to do the same on the right hand side. In that case, the solution set of this inequality wouldn't be affected. If you apply this linear transformation, then the solution set of this inequality would still be the same. Why? Because sigma is a positive value. Do not forget about it. If sigma was negative, then you should have swapped the inequality sign here. Okay, you need to change it. However, sigma is positive. So when you standardize the left-hand side becomes a standard normal random variable, and the right-hand side will become minus 1.65 when you plug in the location value as 78 and the sigma value as 5. Probability that z is less than or equal to minus 1.65 here is what? You are going to calculate that value using the symmetricity of the standard normal random variable. Now, because we know that the PDF of a normal random variable is symmetric around the location parameter, right? And for a standard normal random variable, it is just going to be symmetric around 0 value, okay? So for such a random variable, which has a PDF symmetric around 0, the probability of it to be less than or equal to minus 1.65 is the same probability as the same random variable to be greater than 1.65. Okay, so this is just the left tail probability and this is the right tail probability. And that probability here, the probability of z being greater than 1.65, can be computed by using its complement event. So we subtract the cumulative probability for standard normal random variable to be less than or equal to 1.65 from 1, and that probability is going to be searched through the CDF table for standard normal distribution. Now, we have this CDF table uploaded in the learning management system. Now, we are interested in the probability of our random variable to be less than 1.65, and we are searching the threshold value in the row names and the column names. We have 1.60 here and 0.05 here. The intersection, the cell in the intersection gives you the cumulative probability, which is the area on the left-hand side of the Z value and under the symmetric PDF of the standard normal random variable. Okay, so we have calculated that probability as 0.9505, and we need to subtract it from 1, remember, and the desired probability is 0.0495. The second part of the question is asking this: what kilogram value is exceeded by only 5% of the male students? So we are assuming that there is a certain X value here, there's a certain amount of kilograms. Only 5% of the male students in Özyeğin University is exceeding that kilogram, which means the remaining 95% of the male students, they weigh less than this kilogram amount. So in this part, we say that there is a certain amount of kilograms A such that only 5% of the students are having a weight greater than this value. So the probability of a randomly selected male student to weigh greater than A is 0.05. Or in other words, the probability of a randomly selected male student to weigh less than A is 0.95. So again, we are going to use the standardization procedure to convert this probability statement to a probability statement that is related to a standard normal random variable. So both parts of this inequality is going to be subject to the standardization. The left-hand side will become a standard normal random variable, and the right-hand side will become the unknown A value minus 78 divided by 5. And that probability is going to be 0.95. Now, what we are going to do is we are going to search the CDF table for the standard normal random variable for a 0.95 probability. So this time we are going to search through the probabilities because we are doing the inverse operation here. We are going to search for a probability and we are going to come up with the threshold value. So for which value we get the 0.95 cumulative probability? It is not 1.64 and it is not 1.65. It is just somewhere between these two values. So it's because 0.95 is just in the middle of these two values. It should be 1.645. So we say that for threshold value 1.645, that cumulative probability will be approximately equal to 0.95. So this means a minus 78 over 5 must be equal to approximately 1.645. And this is an equation with a single unknown, and that a value would be 86.225. This means 5% of the male students in Özyeğin University, they have a weight that is greater than 86.225 kilograms. That is the separation point which separates the low weight 95% from the high weight 5% of the male students.